The silence of space has been broken by something that shouldn't exist, something that defies our comfortable understanding of cosmic order. And as it hurtles through our solar system at this very moment, a handful of scientists are asking questions that most of their colleagues wish would simply go away. What if the object we're calling 3I Atlas isn't what we think it is? What if, behind the reassuring label of natural comet, something far more extraordinary is making its way through our planetary neighborhood, performing maneuvers that natural objects simply don't perform, following a trajectory that seems almost too convenient, too deliberate, too perfectly designed to give us just enough time to notice before it vanishes forever into the cosmic darkness from which it came? Harvard University's Avi Loeb has never been one to shy away from uncomfortable possibilities, and his latest suggestion regarding 3I Atlas has sent ripples through the astronomical community that range from intrigued fascination to barely concealed irritation. According to Loeb, while every measurement, every spectroscopic analysis, every data point currently gathered points toward 3I Atlas being exactly what it appears to be, a natural comet from beyond our solar system, we cannot completely eliminate the possibility that this object might be something else entirely. The astrophysicist has gone so far as to suggest that 3I Atlas could potentially be capable of performing gravitational maneuvers, deliberately changing its trajectory in ways that would indicate some form of guidance system, some level of control that natural objects inherently lack. Loeb characterizes this scenario as a black swan event, borrowing the term from statistical theory to describe something that seems virtually impossible until it actually happens, an occurrence so rare and so unexpected that our models and predictions simply have no framework to accommodate it. But unlike most black swan events, which are merely surprising or financially disruptive, the implications of 3I Atlas being anything other than a natural comet would fundamentally alter humanity's understanding of its place in the universe, our perception of cosmic solitude, and, perhaps most unsettlingly, our assumptions about who or what might be watching us from the depths of interstellar space. The story of 3I Atlas began not with a dramatic announcement, but with the quiet, methodical work of astronomers scanning the sky for objects that don't quite belong. The detection systems that caught this interstellar visitor represent decades of technological advancement and international cooperation, networks of telescopes spread across the globe, constantly monitoring the heavens for anything unusual, anything that moves in ways that don't fit the established patterns of our solar system's native inhabitants. When 3I Atlas first appeared in the data, it was immediately clear that something unusual had arrived. The trajectory was wrong, the velocity was wrong. Everything about this object screamed that it had come from somewhere else, from the vast darkness between the stars where objects drift for millions or billions of years in frozen silence before occasionally, very occasionally, stumbling into someone else's solar system. Russian astronomer Vladimir Surdin emphasized just how fortunate researchers were to detect 3I Atlas as it entered our solar system. The universe is unimaginably vast, and interstellar objects passing through our planetary neighborhood are likely far more common than we realize, but detecting them requires that they pass close enough to Earth, that they're bright enough to see, that they arrive at a time when our telescopes happen to be pointing in the right direction, and that their trajectory brings them through the relatively narrow plane of the solar system where our detection capabilities are strongest. The fact that we spotted 3I Atlas at all represents a combination of luck, skill, and the increasing sophistication of our sky survey programs. But having detected it, the question becomes not just what it is, but what it's doing and where it's going. The trajectory of 3I Atlas is what makes this object particularly fascinating to both mainstream astronomers and those willing to consider more exotic possibilities. The comet is moving along what Surdin describes as a shallow trajectory, a path that doesn't simply cut through the solar system in a straight line, but instead takes it past several major planets in a cosmic tour that seems almost designed to provide multiple observation opportunities. On October 3rd, 3I Atlas made its closest approach to Mars, passing by the red planet at a distance that allowed joint Russian and European satellites orbiting Mars to capture detailed observations. The data gathered during this encounter is still being analyzed, but the very fact that an interstellar object passed close enough to Mars to be studied by planetary orbiters represents an extraordinary opportunity for science, the kind of chance encounter that astronomers might wait their entire careers to witness. But 3I Atlas isn't finished with its tour of the inner solar system. Following its Martian flyby, the comet's trajectory will take it near Venus, offering another opportunity for observation, another data point in the growing collection of measurements that scientists are using to characterize this mysterious visitor. Then, in what might be considered the highlight of its journey through our cosmic neighborhood, 3I Atlas will pass relatively close to Earth. The timing of this approach, expected in early November according to current calculations, has generated enormous interest among both professional astronomers and amateur skywatchers, though Surdin warns that observing conditions will be challenging. The geometry of the encounter, combined with the object's brightness and the position of the sun, means that catching a glimpse of 3I Atlas will require careful planning and possibly specialized equipment, and even then, the view might be frustratingly brief and difficult to interpret. The timing of these encounters raises questions that some scientists find intriguing, while others dismiss as pattern-seeking in random data. Why would an interstellar object, originating from somewhere beyond our solar system, follow a trajectory that brings it past Mars, then Venus, then Earth, in relatively quick succession? The conventional answer is simple: gravity and orbital mechanics. The paths that objects follow through space are determined by the gravitational influences of the Sun and planets, and 3I Atlas is simply responding to these forces in predictable ways, following the mathematical laws that govern all celestial motion. Its trajectory past multiple planets is coincidental, a happy accident for astronomers, but nothing more than that, certainly nothing that suggests intent or purpose. But what if the conventional answer isn't the complete answer? What if there's something more to this trajectory than simple gravitational mechanics? This is where Loeb's speculation enters territory that makes many of his colleagues deeply uncomfortable. The possibility of gravitational maneuvers, the suggestion that 3I Atlas might be capable of making small adjustments to its course, represents a departure from everything we understand about comets and asteroids. Natural objects don't steer. They don't make decisions about where to go next. They follow their orbital paths with mathematical precision, slaves to gravity and momentum, incapable of deviation or choice. If 3I Atlas were to demonstrate any ability to alter its trajectory in ways that couldn't be explained by natural forces, it would immediately cease to be a simple comet and become something that demands a completely different framework for understanding. The history of interstellar objects detected in our solar system is brief, but already controversial. Before 3I Atlas, there was Oumuamua, the first confirmed interstellar visitor, which generated its own set of puzzles and debates when it exhibited acceleration that couldn't be fully explained by outgassing or other conventional cometary behavior. Loeb himself was at the center of that controversy, suggesting that Oumuamua's unusual characteristics might indicate artificial origin, perhaps a light sail or some other form of extraterrestrial technology. The astronomical community largely rejected this interpretation, preferring explanations that kept Oumuamua firmly in the category of natural objects, even if those explanations required some creative thinking about cometary composition and behavior. Now, with 3I Atlas making its way through the inner solar system, the same questions are emerging again, the same tension between conventional interpretation and more exotic possibilities. What makes Loeb's position particularly interesting is that he isn't claiming 3I Atlas is artificial. He's simply arguing that we shouldn't completely rule out that possibility based solely on our current observations. There's a subtle but important difference between saying this is definitely artificial and saying we can't definitively prove it's natural. The first claim requires extraordinary evidence, the kind of unambiguous signal or behavior that leaves no room for alternative explanation. The second claim is simply an acknowledgement of the limits of our knowledge, a recognition that our observations, however sophisticated, might not capture every relevant detail, and that dismissing possibilities prematurely can lead to missed opportunities or overlooked discoveries. The concept of a black swan event is particularly apt in this context. Before the discovery of black swans in Australia, European naturalists believed all swans were white, because every swan they had ever observed was white. The assumption seemed perfectly reasonable, supported by extensive empirical evidence, until it was suddenly and completely overturned by a single observation that didn't fit the pattern. In the case of 3I Atlas, the equivalent assumption is that all objects passing through our solar system are natural, that intelligent civilizations don't send probes or craft through interstellar space, or if they do, we've never detected one. This assumption is supported by the fact that every object we've studied has appeared to be natural. Every asteroid and comet has behaved exactly as we would expect natural objects to behave. But what if we're simply looking at white swans and haven't encountered a black one yet? What if the universe contains rare exceptions to the rules we've established, and our inability to imagine those exceptions doesn't make them impossible? The idea that an interstellar object might be artificial touches on one of the most profound questions humanity has ever asked. Are we alone in the universe? For decades, we've searched for signals from space, listened for radio transmissions that might indicate the presence of other technological civilizations, scanned the skies for any hint that intelligence exists somewhere beyond our planet. The SETI program and similar efforts have so far yielded only silence, a cosmic quiet that some interpret as evidence that intelligence is extraordinarily rare, while others suggest simply indicates we're not looking in the right way or at the right time. But physical objects, probes, or craft sent through interstellar space represent a different kind of search strategy, one that doesn't rely on real-time communication, but instead involves sending hardware through the galaxy to explore, observe, and perhaps report back across the vast distances that separate star systems. If an advanced civilization wanted to study other solar systems, sending physical probes would be a logical approach, especially if they had solved the engineering challenges involved in interstellar travel, or if they were patient enough to wait millions of years for their probes to reach distant destinations. Such probes wouldn't need to be enormous or obvious. They could be relatively small, designed for longevity rather than speed, equipped with instruments to gather data and perhaps some form of propulsion for course corrections. Passing through a solar system like ours, such a probe might take the opportunity to swing past multiple planets, using gravitational assists not just for efficiency but for comprehensive observation, gathering as much data as possible before continuing on to the next destination or returning to wherever it came from. This is pure speculation, of course, and it's important to emphasize that there's currently no direct evidence that 3I Atlas is anything other than what it appears to be. A comet from interstellar space composed of ice and rock, following a trajectory determined entirely by natural forces. Every spectroscopic observation suggests typical cometary composition. The object shows signs of outgassing as it approaches the Sun, exactly as we would expect from ice being heated and sublimated. Its brightness and reflectivity are consistent with a natural comet. In every measurable way, 3I Atlas looks like a comet, behaves like a comet, and responds to solar radiation like a comet. The null hypothesis, the default assumption that requires the least extraordinary claims, is that 3I Atlas is exactly what it appears to be. But science progresses not just by accepting null hypotheses, but by rigorously testing them, by looking for anomalies and exceptions that might reveal something new about how the universe works. Loeb's suggestion isn't that we should assume 3I Atlas is artificial, but rather that we should keep that possibility in mind as we continue to study it, that we should look for signs of behavior that can't be explained by natural processes, and that we should be willing to consider alternative interpretations if the data eventually points in that direction. This is how science is supposed to work, by maintaining skepticism toward both conventional wisdom and extraordinary claims, by following the evidence wherever it leads rather than assuming we already know the answers. The scientific community's reaction to Loeb's speculations has been mixed, ranging from respectful disagreement to something approaching mockery. Some of his colleagues have expressed frustration with what they see as sensationalism, a tendency to generate headlines by suggesting exotic possibilities rather than sticking to conservative interpretations. Others have defended his right to raise questions, even uncomfortable ones, noting that scientific progress often comes from people willing to challenge consensus views and consider alternatives that seem unlikely or unpopular. There's a delicate balance between healthy skepticism and closed-mindedness, between avoiding wild speculation and shutting down legitimate inquiry, and different scientists draw that line in different places. What's particularly interesting about the debate surrounding 3I Atlas is that it's not really about this specific object at all. The comet itself, regardless of its nature, will pass through our solar system and depart by the end of December, continuing on whatever trajectory the laws of physics dictate. Within a few months, it will be too distant to observe with any detail, eventually becoming just another dim point of light and then fading entirely from our telescopes as it returns to the darkness of interstellar space. In a very real sense, we have only a brief window to study 3I Atlas, a cosmic opportunity that will close whether we take full advantage of it or not. But the broader questions raised by objects like 3I Atlas, questions about how we search for signs of intelligence, how we interpret ambiguous data, and what counts as sufficient evidence for extraordinary claims, those questions will persist long after this particular comet has departed. The trajectory calculations for 3I Atlas show that its closest approach to Earth will occur in early November, though the exact date and distance depend on precise measurements of the comet's position and velocity. Astronomers are refining these calculations as new observations come in, but the general timeline is clear. We have a limited opportunity to study this object up close, and then it will be gone. This sense of urgency has mobilized observatories around the world, with telescope time being allocated to capture as much data as possible during the critical window when 3I Atlas is close enough for detailed observation. Every available instrument is being brought to bear on this target, from optical telescopes capturing images and spectra, to radio telescopes looking for any unusual emissions, to space-based observatories avoiding the distortions of Earth's atmosphere. What exactly are astronomers looking for? On the surface, they're conducting routine characterization, measuring the comet's size, composition, rotation rate, and outgassing behavior. They're trying to understand where it came from, what conditions existed in its home star system, and what its journey through interstellar space might have been like. But beneath this conventional science, there's an undercurrent of something else, a subtle awareness that they might be looking at something unprecedented. Every observation is being scrutinized not just for what it reveals about cometary science, but for any hint of the anomalous, the unexpected, the inexplicable. No one seriously expects to find evidence of artificial origin, but everyone is aware that if such evidence exists, this might be our only chance to detect it. The challenge of distinguishing between natural and artificial objects at cosmic distances is far more difficult than it might initially seem. In science fiction, alien spacecraft are often depicted as obviously artificial, with clean geometric shapes, bright lights, or clear signs of technology. But real-world detection of artificial objects in space, assuming they exist, would likely be far more ambiguous. An interstellar probe designed for longevity might be covered in ice and dust accumulated over millions of years of travel, making it visually indistinguishable from a comet. Its propulsion system, if it had one, might operate on principles we don't understand, producing effects we might attribute to natural processes. Even deliberate signals might be missed if we're not looking at the right frequencies or if they're encoded in ways we don't recognize. This is the fundamental problem with searching for signs of intelligence in space. We don't know what we're looking for. We can identify the obvious, the things that match our preconceptions about what artificial objects or signals should look like. But truly alien technology, developed by civilizations with different evolutionary histories, different physics knowledge, and different design philosophies, might be so unlike anything we've imagined that we could be looking directly at it without recognizing what we're seeing. The famous quote about advanced technology being indistinguishable from magic applies here, except in this case, advanced technology might be indistinguishable from nature, camouflaged not by deliberate effort, but simply by our inability to recognize the signs of artificiality. Loeb has argued in his previous work that we should be more open to considering artificial explanations for astronomical phenomena, not because aliens are common or because every unusual observation requires an exotic interpretation, but because our current approach might be systematically missing evidence that's right in front of us. The scientific method, for all its strengths, has built-in conservatism that serves an important purpose. It prevents us from jumping to conclusions, keeps us grounded in evidence rather than speculation, and maintains standards of proof that separate reliable knowledge from wishful thinking. But this same conservatism can also make us resistant to paradigm shifts, reluctant to abandon familiar frameworks, even when the data might be pointing toward something new. The history of science is full of examples where initial skepticism toward unusual observations eventually gave way to acceptance of new phenomena. Meteorites were once dismissed as superstitious nonsense, with prominent scientists arguing that rocks couldn't possibly fall from the sky. Ball lightning remains controversial, despite numerous eyewitness reports, because it's difficult to study and doesn't fit neatly into our understanding of plasma physics. Continental drift was rejected for decades before becoming the cornerstone of modern geology. In each case, the resistance to new ideas wasn't due to stupidity or closed-mindedness, but to the reasonable requirement for extraordinary evidence before accepting extraordinary claims. The challenge is distinguishing between the cases where skepticism is appropriate and those where it's preventing recognition of genuine discoveries. In the specific case of 3I Atlas, the evidence for artificial origin is essentially non-existent at present. Everything we've observed can be explained by natural processes. The trajectory, while interesting, doesn't require any unusual forces or deliberate guidance. The composition appears ordinary. The behavior matches what we expect from comets. If this were a court case, the verdict would be clear. Natural object, case closed. But Loeb's point isn't that we should overturn this verdict based on current evidence. It's that we should keep the investigation open, continue collecting data, and remain alert to the possibility that future observations might reveal something unexpected. The phrase black swan event that Loeb uses to describe the possibility of 3I Atlas being artificial carries significant weight. Black swan events, by their nature, are things we don't expect, can't easily predict, and often don't believe until they've already happened. They sit outside our normal distribution of probabilities, in the fat tail of unlikely possibilities that we tend to ignore because they seem so improbable. But improbable doesn't mean impossible, and the consequences of ignoring a black swan event can be severe, whether in finance, politics, or in this case, our understanding of life in the universe. If 3I Atlas were to show signs of being artificial, if observations revealed behavior or characteristics inconsistent with natural objects, the implications would extend far beyond astronomy. It would represent humanity's first confirmed contact with technology from another civilization, even if that contact is indirect, mediated by a probe rather than direct communication. It would prove that we're not alone, that intelligence has emerged elsewhere in the universe, and that at least one other civilization has achieved the capability to send objects between star systems. It would raise immediate questions about the intentions behind such a probe, whether it's simply a scientific mission or something else, whether other similar objects might be passing through our solar system undetected, and whether we should be attempting to communicate with it or study it more intensively. The societal impact of such a discovery would be profound and unpredictable. Some people would find it exciting, confirmation of long-held beliefs that life must exist elsewhere in the universe. Others would find it disturbing, a challenge to religious or philosophical frameworks that place humanity at the center of cosmic significance. Governments would need to decide how to respond, whether to treat it as a scientific curiosity or a potential security issue. The scientific community would face unprecedented questions about protocols and procedures for studying something that might represent another civilization's technology. All of these considerations hang in the background of the 3I Atlas observations, unspoken but present, adding weight to what might otherwise be routine astronomical work. But again, it's crucial to emphasize that we're discussing possibilities, not probabilities, and certainly not current evidence. The overwhelming likelihood is that 3I Atlas is a natural comet, that it will complete its passage through the solar system without revealing anything more exotic than interesting details about interstellar space and the composition of comets formed around other stars. The scientific papers that eventually emerge from this observation campaign will probably focus on conventional topics like dust-to-ice ratios, organic molecule detection, and trajectory refinement. The brief moment of speculation about artificial origin will fade into a footnote, remembered primarily as an example of how even prominent scientists can let their imaginations run ahead of their data. Yet there's value in the speculation itself, independent of whether it proves correct. By articulating the possibility of artificial origin, even as an unlikely scenario, Loeb has reminded the astronomical community to look beyond the obvious, to consider alternative interpretations, and to recognize that our current understanding of the universe, while sophisticated, is certainly incomplete. We don't know everything about how comets behave, about what interstellar space is like, or about what signs of technology we should be looking for. Every observation of 3I Atlas, conducted with these questions in mind, will be more thorough and more careful than it might otherwise have been, and that increased scrutiny benefits science regardless of what it ultimately reveals. Vladimir Surdin's point about the fortunate timing of 3I Atlas's detection deserves further consideration. The universe is vast, and interstellar objects are small and dim. The fact that we've detected 3 interstellar visitors in recent years, first Oumuamua, then 2I Borisov, and now 3I Atlas, says more about the improvement of our survey capabilities than about any increase in interstellar traffic. Our detection networks are getting better. Our algorithms for identifying unusual trajectories are more sophisticated, and our telescopes are more sensitive. As these capabilities continue to improve, we should expect to detect more interstellar objects, providing a growing sample for study and comparison. This raises an interesting question about base rates and probability. If interstellar objects passing through our solar system are common, as improving detection rates suggest, and if even a tiny fraction of those objects were artificial probes, we might expect to eventually encounter one simply by virtue of looking at enough examples. The Drake equation famously attempts to estimate the number of communicative civilizations in our galaxy, but we could construct a similar equation for the number of interstellar probes we might expect to encounter. We'd need to estimate how many technological civilizations exist, what fraction of them send probes, how many probes each civilization sends, how those probes are distributed through the galaxy, and what our detection probability is. The uncertainties in each of these terms are enormous, making any final calculation almost meaningless, but the exercise itself highlights that encountering an artificial interstellar object isn't infinitely improbable, just very unlikely with our current sample size. The shallow trajectory that 3I Atlas follows through our solar system, passing by multiple planets in succession, is geometrically interesting but not particularly unusual. The solar system's planets orbit roughly in the same plane, the ecliptic, so any object passing through this region will naturally have opportunities to approach multiple planets if its trajectory is properly aligned. What's perhaps more interesting is that we detected it early enough in its passage to track it past Mars and will be able to continue observations through its encounters with Venus and Earth. This extended observation window is valuable scientifically, allowing astronomers to study how the comet changes as it experiences different levels of solar radiation, how its outgassing evolves, and whether its trajectory requires any adjustment to the initial calculations. Trajectory refinement is a normal part of tracking any solar system object, whether it's a comet, asteroid, or spacecraft. Initial observations provide approximate positions and velocities, which are used to calculate a preliminary orbit. As more observations accumulate, the orbit is refined. Uncertainties decrease, and predictions become more accurate. For an object like 3I Atlas, coming from interstellar space with no prior observations, this refinement process is particularly important. Any deviation from the predicted trajectory needs to be explained, either by better understanding of gravitational influences, by non-gravitational forces like outgassing, or, in the most extraordinary case, by deliberate course changes that would indicate artificial control. Non-gravitational forces are actually quite common in comets and can significantly affect their trajectories. As a comet approaches the sun and heats up, ice sublimates into gas, creating jets that act like tiny rocket engines, pushing the comet in directions that depend on its rotation and the location of active vents. These cometary non-gravitational forces are well studied and understood, but they can be difficult to predict because they depend on details of the comet's surface and interior that we often can't observe directly. For 3I Atlas, astronomers will be carefully monitoring any trajectory deviations and comparing them to expected non-gravitational effects. If the deviations are consistent with normal cometary behavior, that's evidence for natural origin. If they're not, that becomes interesting and requires further investigation. This is where the speculation about gravitational maneuvers enters the picture. A truly controlled object, a probe with active guidance, would be capable of making trajectory adjustments that don't correspond to expected non-gravitational forces from outgassing. These adjustments might be subtle, small course corrections rather than dramatic changes, but they would show up in precise astrometric measurements as unexplained accelerations or trajectory shifts. Detecting such maneuvers would require extremely careful observation and analysis, ruling out all possible natural explanations before considering artificial ones. It's the kind of claim that would need overwhelming evidence because it challenges fundamental assumptions about what we're observing. The observation window for 3I Atlas is limited by both geometry and physics. As the comet approaches the Sun, it becomes brighter due to increased solar illumination and outgassing activity, making it easier to observe. But this improved visibility comes with a cost. The comet is also getting closer to the Sun in the sky, making observations difficult due to the Sun's overwhelming brightness and the limited time when the comet is visible above the horizon in darkness. This is what Surdin means when he warns about unfavorable visibility conditions around the time of Earth's closest approach. Astronomers will need to make careful use of the available observation windows, capturing data when the geometry allows, and combining observations from multiple locations around the globe to maximize coverage. After its passage through the inner solar system, 3I Atlas will begin its long journey outward, eventually crossing the orbits of the outer planets and returning to interstellar space. By the end of December, according to current calculations, it will have left the boundaries of the solar system, though defining exactly where those boundaries lie is somewhat arbitrary. Is it the orbit of Neptune, the heliopause where the solar wind meets the interstellar medium, the edge of the Oort cloud, if one exists? Regardless of the definition, the practical reality is that by late December, 3I Atlas will be too distant for detailed observation, and our opportunity to study this interstellar visitor will effectively be over. This finite window for observation adds urgency to the current campaign, but also highlights a broader issue with interstellar object studies. We're always racing against time. Unlike asteroids and comets native to our solar system, which orbit the Sun and can be observed repeatedly over years or decades, interstellar objects pass through once and are gone forever. Every observation must be made during their brief visit, and anything we miss is missed permanently. This makes the decision about what to observe and how to allocate limited telescope time particularly critical. Do you prioritize conventional characterization, gathering as much data as possible about composition and physical properties? Or do you allocate some resources to looking for the unusual, the anomalous, the potentially artificial, even though the probability of finding anything is extremely low? Different observatories and different research groups are making different choices about these priorities, which is healthy for science. Some are focused on the conventional characterization that will definitely yield publishable results and contribute to our understanding of cometary science. Others are willing to take risks on more speculative observations that might reveal something extraordinary or might reveal nothing at all. This diversity of approaches increases the chances that if there's something unusual about 3I Atlas, someone will notice it, while also ensuring that the basic scientific work gets done, regardless of whether the object turns out to be exotic or ordinary. The ironic reception that Loeb's speculations have received in some quarters of the scientific community reflects a genuine tension in how science operates. Science values skepticism, evidence-based reasoning, and conservative interpretation of data. These values serve important functions, preventing the field from being overrun by speculation and maintaining standards that distinguish scientific knowledge from pseudoscience. But science also requires creativity, willingness to consider new ideas, and occasional paradigm shifts when evidence demands it. The balance between these competing needs is never easy to strike, and different scientists have different comfort levels with speculation and unconventional ideas. Loeb's high academic standing and significant contributions to astrophysics, which his colleagues acknowledge even while disagreeing with his speculations about interstellar objects, provide him with credibility that allows his ideas to receive attention rather than immediate dismissal. A less established scientist making similar suggestions might find their ideas ignored or their career prospects damaged. This reveals both a strength and a weakness in how science operates. Reputation matters, providing established scientists the freedom to take risks and propose unconventional ideas, but also potentially creating barriers for newcomers with different perspectives. In an ideal world, ideas would be evaluated purely on their merits, independent of who proposes them. But in practice, the source of an idea influences how seriously it's taken. The artificial origin hypothesis for 3I Atlas or similar interstellar objects connects to broader questions about the search for extraterrestrial intelligence and what forms that search should take. Traditional SETI focuses on electromagnetic signals, searching for radio or optical transmissions that might indicate technological civilizations. This approach has the advantage of being able to detect civilizations at vast distances, potentially across the entire galaxy, but requires that those civilizations are actively transmitting signals we can detect, using technologies and protocols we can recognize. The search for artifacts, whether interstellar probes or other physical evidence of technology, represents a complementary approach with different strengths and weaknesses. Artifacts have the advantage of being potentially detectable even if the originating civilization is no longer transmitting, has become extinct, or uses communication methods we haven't imagined. A probe sent millions of years ago might still be functioning and detectable long after its creators have disappeared, but artifacts are also much harder to find because they're small, localized, and, unless they're in our immediate neighborhood, effectively impossible to detect with current technology. We can search the entire electromagnetic spectrum for signals, but we can only search for artifacts in the relatively tiny region of space we can directly observe, essentially our solar system and its immediate surroundings. The suggestion that some interstellar objects might be artifacts essentially proposes that we add artifact detection to our existing survey programs for comets and asteroids. We're already looking for these objects for planetary defense and scientific purposes, so adding an additional layer of analysis to check for artificial characteristics represents relatively little additional effort or cost. The main barrier isn't technical or financial, but conceptual, convincing the astronomical community that this kind of search is legitimate science rather than fringe speculation. Loeb's advocacy for considering artificial explanations for unusual interstellar objects can be understood partly as an attempt to shift this conceptual framework to make artifact searches a respectable part of mainstream astronomy rather than something pursued only by outsiders. Whether or not 3I Atlas reveals anything unusual, its passage through our solar system serves as a reminder of how much we still don't know about the universe beyond our immediate neighborhood. Interstellar space, the vast regions between star systems, remains largely unexplored and poorly understood. We can make educated guesses about conditions there based on our understanding of physics and observations of our local environment, but direct sampling is extremely limited. The Voyager spacecraft, humanity's most distant ambassadors, have crossed into interstellar space, but remain close enough to the Sun that they're still within the Sun's influence in many ways. Objects like 3I Atlas, forged in other stellar systems and spending eons traveling through true interstellar space, carry information about those distant environments encoded in their composition and physical properties. Every measurement of 3I Atlas contributes to a growing database of interstellar object characteristics that will eventually allow statistical analysis and comparison. With only 3 confirmed interstellar objects detected so far, we can't yet draw broad conclusions about what's typical and what's unusual. But as detection rates improve and the sample size grows, patterns will emerge. We'll learn about the diversity of planetary systems, about the efficiency of different mechanisms for ejecting objects into interstellar space, and about what happens to those objects during their long journeys between stars. This knowledge will inform our understanding of planet formation, stellar system evolution, and the transport of material through the galaxy. The timing of 3I Atlas's visit, in an era when humanity has sophisticated instruments for studying celestial objects but hasn't yet developed interstellar travel capabilities, is itself interesting to contemplate. If we had detected this object a century earlier, we would have been limited to simple visual observations, unable to determine its composition or characterize it in detail. If we detect similar objects a century from now, we might have the capability to send fast probes to intercept them, to study them up close, or even collect samples for return to Earth. We exist in a narrow window where we can detect and characterize interstellar visitors, but cannot yet interact with them physically, a transitional state that colors our perspective and capabilities. Some researchers have proposed the concept of interstellar archaeology, the search for artifacts or evidence of other civilizations, not through electromagnetic signals, but through physical remains. This could include interstellar probes, but might also encompass other forms of evidence like industrial pollution in the atmospheres of exoplanets, megastructures that modify starlight in detectable ways, or waste heat from large-scale engineering projects. The advantage of this approach is that many artifacts would be detectable long after their creation, potentially giving us access to evidence from civilizations that existed millions or billions of years ago. The disadvantage is the enormous challenge of distinguishing artificial from natural phenomena at cosmic scales and distances. 3I Atlas, in this context, represents a test case for interstellar archaeology methods. Can we develop criteria for identifying artificial objects among the population of interstellar visitors? What observations would be necessary to make a convincing case? How do we balance the desire to remain open to unexpected discoveries against the need to avoid seeing patterns where none exist? These are not just abstract philosophical questions, but practical methodological issues that will shape how we search for evidence of other civilizations in the coming decades. The December departure of 3I Atlas from the solar system will mark the end of our opportunity to study this particular object, but it won't end the broader questions it raises. Future interstellar objects will be detected, each offering another chance to refine our understanding and test hypotheses about what these visitors from beyond might reveal. Each observation campaign will be slightly better prepared than the last, with improved instruments, more sophisticated analysis techniques, and growing experience in how to maximize the limited observation windows available. Over time, interstellar object astronomy will mature from its current state of opportunistic observation into a more systematic discipline with established protocols and expectations. Whether any of these future visitors proves to be artificial remains an open question, one that may not be answered in our lifetimes. The universe is vast, and even if technological civilizations are common, the probability of their probes passing through our specific location in space at this specific moment in time is low. We may be searching for black swans in a universe where they're so rare that encountering one remains forever unlikely. Or we may be on the verge of discoveries that will transform our understanding of our place in the cosmos. The only way to find out is to keep looking, keep questioning, and remain open to possibilities that our current understanding suggests are improbable, but not impossible. As 3I Atlas continues its journey through our solar system, past Venus, and toward its November encounter with Earth, it carries with it the hopes and questions of scientists around the world. Most expect it to reveal nothing more than interesting cometary science. Some hope for something more, for an anomaly that demands explanation, for evidence that we're not alone. All recognize that this moment, this brief window, when an object from another star system passes through ours, represents an extraordinary opportunity to learn something new about the universe. Whether that new knowledge confirms our existing understanding or challenges it in unexpected ways remains to be seen. The observations continue, the data accumulates, and the cosmic visitor draws closer, carrying secrets that may be entirely ordinary or utterly extraordinary, and we won't know which until we look. The coming weeks will tell us more about what 3I Atlas is and what it isn't. The astronomical community waits with instruments ready and minds open, prepared for routine results, but alert to the possibility of surprise. In the meantime, the comet continues its ancient journey, following a path determined by forces we understand, or perhaps, in the most unlikely and consequential scenario, by intentions we have yet to discover. Either way, the story of 3I Atlas will add another chapter to humanity's growing understanding of the universe beyond our world, a universe that continues to surprise us with its complexity, its beauty, and its mysteries.